This section we're going to look at chemical reactions that make a precipitate. Well, in this case, a precipitate is just, that's my cat, say hi cat. In this case, a precipitate is simply another word for a solid. The four main types of reactions that we look at in Chapter 8 are reactions that make a solid, and yes, this little yellow stuff that's pictured in here, this is a solid. I know it seems really strange that that is a solid, but it is. But the particles are about as fine as the particles you would find in, say, powder. So it doesn't look like a solid as you would typically expect a solid to look, but it is. It really is. We call it a precipitate. We're going to be looking at reactions that form water. These are acids and bases. When you put an acid with a base, you're always going to get salt and water. So this is a reaction that forms water. In this chapter, we're also going to be looking at how a gas is made or evolved. So when you mix two things together and look, bubbles, you're going to make a gas. We're not going to spend a lot of time on those. And we're also going to look at reactions that transfer electrons, kind of like the story behind an ionic compound. Now, to have a precipitation reaction, the first thing you need to do is have dissolved ions. So here we have table salt. You take table salt. Here it's a nice little solid. You can see the array of ionic bonds. Well, that wouldn't be a bond. Here's a bond, and here's a bond. Do you remember what the name of this is called? Yes, these are all electrostatic attractions. I've heard some people say this isn't a real bond because a bond is supposed to be sharing of electrons, and clearly there's no sharing going on. However, whether it's classified as a bond or not in your textbook doesn't really matter. They are bonded in my textbook. And since I'm the one grading your test, whatever. Anyway, you got to get these ions dissolved. So here we have dissolved ions in the solution. So that's a requirement. And if you notice how it dissolves, it's really kind of cool because in this picture you can see the sodium has a positive charge and the water has a negative side to it. So the water kind of surrounds the positive cation and sort of hides it from view. And chlorine, this side of the water, is positive and it completely surrounds this negative chlorine ion. And then it kind of hides it. It's called hydration. When you mix two ions who don't want to be hydrated but like each other more, you end up with a precipitate. A precipitate is a fancy chemistry word simply meaning a solid forms in the solution. There's a precipitate, and there's another precipitate. Okay, this is the entire story for how to make a precipitate reaction. And if it doesn't completely make sense this first time, don't worry, I have several more examples coming at you. So here we go. The first one I'm going to take a look at is silver nitrate. Silver nitrate, when you put it in water, does dissolve. And how does it dissolve? Well, it's called a dissociation. Dissociate means to break apart. There's the word dissociate, which means it's going to break apart. So we're going to take silver nitrate and I'm going to draw an arrow showing that it's going to break apart into silver ions and nitrate ions. And what it really looks like in the water, oops, lost my pen, there it is. What it really looks like in the water is that. Now this big 2 is out here, this big coefficient 2, because of the balanced equation. So don't worry about that right now. The second solution I have is potassium chromate. And it too, you need to write a dissociation for potassium chromate. It'll make your life so much easier. So then we end up with 2 potassium ions and 1 chromate ion. And that's what's going on in the solution. Of course, you know, there's a lot more ions in it than just 2 or 4. You got probably many moles worth, but we're just going to pretend. When you mix these two together, you get a chemical reaction. One, you know there's a chemical reaction because look, there's a solid here or a precipitate. Either one, doesn't matter. So, well, what's our products? It will be your job to figure out what the products are. Well, we started off with silver. And we know silver's somewhere over here in the product side because, you can't disappear ions. So who is the silver going to hook up with? Is it, because, the silver dissociated from nitrate. It totally broke up with nitrate, didn't like it anymore. So who's it going to hook up with? Potassium? Or is it going to hook up with chromate? Well, if you said chromate, you are right. But why? Because in an ionic compound, you have to have a cation, positive, and an anion, negative. And when you make an ionic compound, those charges have to add up to 0. So what would the chemical formula be for silver chromate? There you go. So now we have to look at what's left over. Who else got together? Well, sodium was here, not sodium, that's funny. Nitrate is here, and potassium's here. So what's the chemical formula going to be for potassium nitrate? That is correct. Well, the next thing you have to answer is who's the solid? In this case, our solid was silver chromate. And if you're asking, well, how are you supposed to know that? That information's coming in a whole big list of solubility rules. I'm going to finish this chemical reaction by writing AQ here, AQ here, a solid here, and AQ here. Those are the basics. We're going to do several more of these together, so be patient with yourself and with me. Okay, one of the biggest questions students have in regards to these types of problems is what is going to go with what? Now, your picture on your packet has a couple has some arrows on it, and the arrows are really stupid, so totally and completely disregard those arrows. I don't know who put it together, but if I'd caught it earlier, I would have fixed it on your packet, but I didn't, so we have to deal with it. In an ionic compound, we know that the first one is always positive and the second one's negative. And this one's positive and this one's negative. Well, who's going to hook up with whom? A can only hook up with a negative. See, A and B broke up and A doesn't want anything to do with B anymore. So A now is going to go and hook up with D. So that gives us this compound, AD. Well, now that C and D have broken up, C is only going to hook up with B. That's the only one available because opposites attract. These reactions are called double displacement reactions. I kind of like to think of it as that TV show, Wife Swap, where you swap them out. Or high school. Could just be high school, couldn't it? Oh, well, maybe. Let's look at another one. So in this picture, A is positive. Hold on, find my ink. Where's my pen? There it is. A and B and C and D. So A has to hook up with D. That's the only one left. So this picture's really stupid too. Gosh, we're going to ignore this picture. Ignore it altogether because there's no way that's right. But if you can give me some extra credit points about why this picture is totally not possible, yeah, I have some serious extra credit if you can tell me what's wrong with this picture because it's just flat not right. I'm sorry I didn't catch it, but this one's pretty good. See, if this one, hold on, erase all the ink on the slide. Erase all ink on slide. Okay, here we go. So we'll try this one. This one looks good. So we know that this guy is positive and she's negative. And this guy is positive and she's negative. And oh, look, it's wife swap because this positive guy ended up with her. And this positive guy ended up with her. Now there's a good double displacement reaction. This picture shows yet another double displacement reaction. So let's take a look at what we have in this test tube. We happen to have silver nitrate in this test tube. Silver nitrate will dissociate in water to silver ions and nitrate ions. So let's take a look. We have silver nitrate, and there's your ions. In this test tube, we have potassium chloride. This will dissociate into potassium ions and chlorine ions, which is right there. When we mix these together, a precipitate forms, solid, which is a precipitate. In this case, the precipitate is silver chloride, because silver can only hook up with the chlorine ions. Silver dumped nitrate, doesn't like nitrate at all anymore. Nope, told it to bug off. It can't hook up with positive potassium. No, that can't happen. So the only one left is chlorine ions. So you end up with silver chloride, leaving potassium and nitrate ions floating around in the solution. So if I were to actually write this the way it should be, potassium nitrate is aqueous. Potassium, well, I said potassium again. Silver nitrate is aqueous. Potassium chloride is aqueous. Silver chloride is your solid. And potassium nitrate is aqueous. Looking at yet another double displacement reaction. In this container, I put lead to nitrate. Well, let's take a look at the ions. Lead to nitrate will dissociate into lead ions and 2 nitrate ions. So that's what's floating around in the solution. In this container, I happen to have sodium hydroxide. Well, sodium hydroxide will dissociate into sodium ions and hydroxide ions. So that's what that looks like. When I combine these two together, what do you think's going to happen? Well, I do end up with a solid, and I end up with ions still floating around in the solution. Who do you think the lead is going to hook up with? Because it told nitrate to bug off, so it's not going to hook up with nitrate again. So, is it going to be the sodium or the hydroxide? That's correct. It's going to hook up with the hydroxide because it has a negative charge. Now to make the compound, look at this. We have lead with a 2+ charge. We have hydroxide with a -1 charge. So the formula is going to have to include 2 hydroxides, like that. Leaving in the solution, now we have to put sodium with nitrate. I don't care about this 2 at all to make the compound. It doesn't matter. You simply look at the charges. So the formula for sodium nitrate becomes NaNO3. This arrow, notice that appeared out of order, is pointing at this black solid, this precipitate that is in the solution. How on earth did we know that the lead hydroxide was the solid and that these ions are still floating around in the solution? There's the question. That's what we're going to use our solubility rules to determine. I gave you a list of solubility rules, and good news, you'll be able to use that list on the test. Yay, you don't have to memorize them, you just have to know how to use them. This is funny. This is the list from your textbook. And notice it says most nitrate salts are soluble. For our purposes, we're going to go with all of them. And when I say nitrate, I also mean nitrite. And most, and for our purposes, you can go with all, are also soluble. The word soluble, this word means it dissolves. Insoluble, where did insoluble go? Oh, well, it's on there somewhere. Insoluble means it does not dissolve. And for our purposes, insoluble and slightly soluble and moderately soluble all mean the same thing. Insoluble means it's going to make a precipitate or a solid, if you will. Each one of these rules is more important than the one after it. Now this is my shorthand version of the solubility rules. These things are soluble. Nitrates, nitrites, they're always soluble. If it's in column 1, it's soluble. If it contains chlorine, it's soluble, except silver chloride, lead 2 chloride, and mercury 2 chloride. These are all insoluble. You do not need to memorize that, but you do know how to use the chart I gave you. Sulfates are always soluble, except those with barium sulfate, lead 2 sulfate, and calcium sulfate. Those are insoluble. That pretty much covers the solubility rules. In general, like I said, this is the shorthand version. Now let's take a look at the insoluble side of things. Hydroxides are insoluble. Well, wait a minute. What if I have something like sodium hydroxide? Is that going to be soluble or insoluble? Because look, sodium is here from column 1 and hydroxide's down here. So what is it? If you said soluble, you are correct, because this rule about column 1 is more important than the rule regarding a hydroxide. So the top rules, well, they rule. Sulfides are also insoluble, unless of course it's with column 1. Phosphites and phosphates, I'm going to put a 4 here like it should be, are also insoluble. Carbonates, insoluble, unless of course it's hooked up with something from column 1. Potassium carbonate, soluble or insoluble? It's soluble because potassium comes from column 1. Let's take a look at another double displacement reaction where we have to figure out who the solid is. So, potassium chromate. Potassium chromate dissociates into, let's see, do an arrow. I'm just going to cheat here and write 2 potassium ions and 1 chromate ion. So here we have 2 potassiums and 1 chromate. Barium nitrate will also dissociate into 1 barium ion and 2 nitrate ions. So in the picture you can see we have 1 barium ion and 2 nitrate ions. Well, when we mix these guys together, we end up with barium chromate. Well, let's see. Potassium had to hook up with nitrate. That's the only way it would work. And to make that compound, you only pay attention to the charges. The coefficients only matter for balancing a chemical equation. They don't matter for making formulas. And the barium could only hook up with chromate. So barium chromate and potassium nitrate. Look at your solubility rules. Notice it says everything from column 1 is always soluble. And it also said nitrate ions are also always soluble. So next to the nitrate, we're going to write AQ. And next to the barium chromate, well, that's our precipitate.
Oven's going off.
And my oven's going off, so I'm going to take a pause and go put dinner on the table. The previous slides showed the ideas behind the problems. This one actually shows the problems, what they look like, and what you're going to be expected to do. So go ahead and pause the video so you have a moment to read through it and see if you can write the entire balanced equation all on your own. And then when you think you have it or you're just plain stuck, go ahead and restart the video and we'll see if you nailed it. I was looking for my pen. That's what that was. All right, so here we go. We start off with silver nitrate. So we know that silver nitrate, well, let's see, silver has a +1 charge. Nitrate has a -1 charge. So when we put that together, we get silver nitrate. Plus, now we need potassium chloride. Potassium has a +1 charge, and chlorine has a -1 charge. So that formula is KCl. Now we have to figure out our two products. Since silver's a positive charge, this cation has got to find an anion to hook up with. That's this one. So we end up with silver chloride. Plus, well, here's the cation, so it's got to hook up with the anion. Potassium nitrate. Well, I know that this is aqueous, as you can clearly see. It's totally dissolved. This one's aqueous. It too is totally dissolved. But what is this precipitate? Well, take a look at your solubility rules. Potassium ions are always soluble in water. Nitrate ions are always soluble in water, so that's aqueous. Chloride ions are always soluble in water except when hooked up with silver. Oh, ding, ding, ding. There's your solid. That's your precipitate. So here are the steps really that you're going to need to do to solve these problems. The first step is you need to write the reactants as complete formulas, like Ag plus SO4 2 negative. As a complete molecular formula, you would end up with Ag2SO4. The second step that you'll do then is to exchange the anions. So if this is one of ours, and then say the other one is sodium chloride. Well, we know sodium has a plus, that's a negative, so we're going to exchange the anions. The silver is going to hook up with the chlorine, and the sodium then will hook up with sulfate. Then we have to find out which one is the precipitate using the solubility rules. And I guess we could have a step 4 on there that says balance the equation. Let's practice another problem. Okay, take a minute, read through the video, pause it, see if you can do it. Okay, well this first one says barium nitrate. Well, barium has a 2 positive charge. Nitrate has a -1 charge. So your formula is BaNO3 2 plus. Now our next one is sodium sulfate. Sodium, and then we have sulfate. And by the way, it's a really good idea to write the ions separately. It'll make your life so much easier. So the formula for sodium sulfate, we have Na2SO4. Now, both of those are aqueous. I'll write aqueous here. Now, exchange the anions. Barium has went and dumped nitrate, and so the only one it has left to hook up with is sulfate. So we end up with BaSO4 plus, well, sodium then is going to hook up with nitrate, NaNO3. Using your solubility rules, you should know that both sodium and nitrates are never, ever, ever going to make a precipitate. Sulfates are soluble, unless, of course, they're hooked up with, bingo, barium. Now, the last step you have is to balance the equation. Well, I've got 2 nitrates here, so I need 2 nitrates there. 2 sodiums, well, there we have 2 sodiums. Well, I'll be darned, we're balanced. Again, pause the video, see if you can do this one on your own. All right, lead 2 nitrate, so that means Pb with a 2+ charge, and nitrate with a -1 charge. So that formula is Pb parentheses NO3 and parentheses 2, it is aqueous, plus. And then we have potassium iodide. Well, there's the potassium ion and the iodide ion, so Ki. That one's also aqueous. Mixing those together means swap the ions. So lead's going to hook up with iodine, so your formula is PbI2 plus, then we have potassium with nitrate. So then KNO3. Well, this one's aqueous. And iodine behaves just like chlorine. So lead, lead 2 iodide actually, is, oops, I should write that correctly, is your solid. And you are done with, oh wait, we got to balance it, don't we? Well, let's see, let's put a 2 here, then a 2 here. Okay, now we're balanced. It's all good. All right, here's one for you to try on your own. This one I'm expecting to see this one, so please give this one a try. Here we go. We have sodium sulfate. So I'm going to write the ions because it's really helpful. That's why. So Na2SO4, it is aqueous because sodium's always aqueous. And then we have potassium chloride, so we end up with, we should put those up here, K plus and Cl minus. So KCl, and that one's aqueous. Yields, well, let's swap the ions, so I end up with sodium chloride and potassium sulfate. So which one forms a solid? Well, let's hope you did that for this one. Look at that. No precipitate. Theoretically, or technically, this one had no chemical reaction because at the end, you only have all 4 of these ions floating around in the solution. Nobody hooked up. So yes, it is possible not to have a precipitate. All right, these next several problems are extra credit for you to go and try on your own. Well, up next we have molecular equations, complete ionic equations, and net ionic equations.